Good afternoon, everybody. Let's get started with the class. So I am doubly remote today. So if you have any problems seeing anything I'm putting on the screen, please let me know. Shoot me a chat. And if I don't see your chat, please shout it out by unmuting. So for announcements, please see the Canvas page for the upcoming assignments. You have homework 1 coming up soon. That due date and due time are posted there. Lab 1, the first lab, will be this Friday, and you will form groups of 2. So you'll have one lab partner, and you'll start uh, designing and building your test bed structure for the constant speed propeller project that we're going to talk about. I'll give you an overview of that this Friday in lab. So let's get started on the material. During the last class, I started off with a review. We're going to spend a couple more lectures on review. I want to make sure you have a good foundation on some of the original or initial circuit theory that you've seen before, but show you some practical applications, especially when you might run into some of these problems during your project or future projects. And we're going to, let's see, last time we talked about circuit theory, we focused on some applications. We ended with calculating energy delivered to a device, and we also talked about resistance of a wire. And I want to show you a practical application of that today with solar panels and power efficiency. So last time we talked about wire resistance, and I mentioned how, well, wires aren't ideal, and you're always going to have some resistance, and sometimes that matters. And sometimes you actually have to measure some really low resistance values. We saw this last year during the project when we bought some breadboards, and actually a lot of breadboards will do this. If you try to have more than a few milliamps run through the blades of a breadboard, you might see significant voltage drops. We were seeing that last year, which is why we're going to a printed circuit board this year. You'll see those in lab this year. But let's suppose you have this wire under test. When you measure a wire, the problem is that you also have wires coming from the test leads that may have their own resistance, and they contribute to voltage drops, especially when you have higher current. If you're just dealing with a few milliamps, that's usually not a big deal. Once you get up into the amp range or higher, then some of these thinner gauge wires can cause a problem. So let's suppose you have a power supply set for constant current. Here it's set for 2 amps current, and I connect test leads to this wire. Then what I would do, and what I did for measuring voltage across this wire, is take the voltmeter and connect it directly across the wire, because what you'll see is that although there's 0.128 volts across the wire, if you go back to the other side of the test leads, we have 0.4 volts measured with a voltmeter. Okay, so that means that there's a voltage drop there across the test lead. So 0.232 roughly voltage drop is across the test leads. Okay, and that's actually more than the voltage across the wire you're trying to test. So that's going to give you a bad measurement and a bad calculation of wire resistance. So the point here is that notice that where you measure voltage matters, especially when dealing with higher current. And I'm going to call out when we get to test equipment that measures resistance that there's actually a 4-wire test where you have to use 4 leads connected to the ohm meter in order to get a good measurement of a low resistance load. And notice here that some power supplies like this one have voltage measurements and current measurements. And oftentimes they're either not so accurate, they're not as accurate as a voltmeter, or an ammeter that's designed to be a voltmeter or an ammeter. Or sometimes there's resistance internally or in the junction to the test leads that causes a voltage drop. So measuring or where you measure voltage matters in high current situations. And high current, again, is if you're using thin test leads, then an amp or above matters. Okay, so this voltage drop comes from resistivity of the material used for the wire. So the resistance of a wire can be calculated and characterized using a resistivity value called rho. It's in units of ohm meters. And so if you have a wire of length L and that wire is made of a metal with resistivity rho, right, here's the resistance R in ohms, resistivity rho in ohm meters, length in meters, cross-sectional area in meters squared. The resistance of that wire is rho L over A. It's kind of what you would expect, right? Because you would think that the longer a wire is, the higher the resistance would be. And the thinner a wire is, or lower cross-sectional area, the higher the resistance would be. And that's reflected here in this relationship shown. So resistivity is a characteristic of the metal. It depends on the material. And what you'll see is in the past, there was a lot of wire that was just copper, but you'll see now there's some wire that's copper coated aluminum. And basically it makes it cheaper to produce. And aluminum has a worse resistivity. It's a higher resistivity compared to copper. So you got to pay attention to what kind of material you're using or what kind of material the wire is made of. When you're calculating resistivity and you're trying to figure out what is the voltage drop between your power source and the load. The resistivity of copper is this, 1.72 times 10 to the negative eighth ohm meters, and that's at 20 degrees C. I'll show you some information on that. So here's an example. If you have 1,000 feet of copper wire, and it's 12 gauge wire, we'll talk about 12 gauge wire. It has a diameter of 0.0808 inches. And so let's calculate the resistance of that wire. So here's the resistivity. There's the copper wire resistivity. Length is 1,000 feet. Let's convert that to meters. The wire diameter is 80 mils, 80.8 mils, 80.8 thousandths. All right, that's the value in meters. So the area is this in meters squared, and that means rho L over A is 1.5 ohms. So you get about 1.5, 1.6 ohms of resistance across this 12 gauge wire, which again can be a problem if you have high current going through that wire. Okay. So that's the resistance per 1,000 feet you can calculate for this wire, and then you can scale from there for your application. It's common to give wire resistance in ohms per 1,000 feet. So you don't have to use the property of the material. You can just look at the specification for the wire. Okay. You will see, especially when I'll show you a table of wire gauges, but some equations use circular mills, and that's a constant that accounts for the resistivity and the length units, specifically the ratio of area between a square and a circle, to make life easier. So you'll see this sometimes. If you're given circular mills, you get a constant, you get an area in circular mills and a length in feet, and this is how you calculate resistance of a wire given those parameters. But I don't see that often, but you will see it in the table I show you next. Okay, so here's wire gauge. This wire gauge table I'm going to show you is American wire gauge. It applies here in the States. International versions may vary, but we use AWG here, sometimes just called gauge. So a common way to specify the diameter of a solid round electrical wire is with gauge, American wire gauge. Okay, and you'll see resistance in tables associated with those gauges. And they typically specify, like we calculated on the last slide, ohms per 1,000 feet at various temperatures, right? There's a difference if you have a copper outside versus copper under the hood of a car, which is much different temperature. Here's a table. You can find these tables in various forms, but on the left, you see the wire gauge, right? Here's 0, 1, 2, 3, 4. As you go up in number on wire gauge, the wire gets thinner. As you go down, the wire gets thicker. And if you want thicker than 0, you go to double aught or triple aught or quadruple aught. Okay, so then here you'll see diameter in mils. Mils is thousandths of an inch, right? So I will use mils and thousandths interchangeably. Here's that circular mils unit, square inches, and then here along the top you have temperature, and then the resistance per 1,000 feet for those temperature columns. And for example, a 14 gauge wire has, let's see, it's its diameter, 64 mils, so 64 thousandths. And that's the area. And so at 20C, it's 2.5 ohms per 1,000 feet. Okay. So room temperature, that's what the resistance is. And resistance increases with temperature. Okay. So then this is for solid wire. For stranded wire, if you're using that, then the cross-sectional area is the equivalent area of a solid copper wire. So the stranded wire is going to be a larger diameter for the same resistance per 1,000 feet for the same gauge. Okay. All right. So let's talk about a practical example. This is like Ohm's law and tables, and why does this matter? Well, here's an example that I actually ran into. And if you ever go off grid or install an array of solar panels on your house or wherever, right, your cabin, then you will likely run into this issue. Let's suppose, for example, you have 4 solar panels, okay, and then you have a load. You want to power this load with a solar panel controller. The solar panel controller does lots of things. It takes in a wide range of voltage from the solar panel, and it outputs usually a charging voltage for a battery, and then the battery connects to the loads or a power inverter, which converts the DC battery voltage to AC for AC loads. Okay, and let's suppose that load is 50 feet away from the solar panels. And maybe these wires run down the house, or they run from your cabin, or your off-grid camping trailer is in the shade and you're 50 feet away. So this is a reasonable distance. Okay, and you're trying to decide on wire gauge. And in circuits class, it doesn't matter, right? All wires are perfect conductors. And so you'll see it matters here. So each panel is nominally 100 watts at 18 volts for this particular panel that I chose. And that's the sun's power roughly, in just bright sun roughly is a kilowatt per square meter. At 20%, 23%, you get about 200 watts out of a square meter. And so this is probably a half square meter panel with a voltage of 18 volts. And there's various ways you can connect solar panels together. And one way is to put them all in parallel. So if I have 18 volts at each of these panels terminals, I can connect them all in parallel. And so I'm joining all 18 volts, right? All panels together, producing 18 volts here. That's a reasonable way to do it. You can do that. And so each panel will contribute current, which will flow out of each of its red leads, the positive leads, down to the power to the charge controller, and then back to the panel. Okay. And so you have, if you have four 100-watt panels, you have 400 watts total at 18 volts. So the question becomes, well, we talked about high current is a problem through thin gauge wire. Here, you have a current of 22 amps. So you have 400 watts at 18 volts. So, voltage changes depending upon solar conditions and how much load you apply to the solar panel. But let's use this as a rough estimate of 22 amps. So you have 22 amps coming from those panels going to the right through the red wire, black to the left through the black wire, supplying your charge controller and load. And let's suppose the charge controller maximum input voltage is 100 volts. Typically, these charge controllers have some maximum voltage. You go higher than that, you destroy them. Okay. Now you're choosing wire, and so you're looking at this $72 for 50 feet of wire, red black wire. It's meant for a solar installation, and it's 14 gauge. Okay. And so let's figure out, well, is this going to work? And what do I mean by work? It means, are you going to waste all of your power, or how much of your power are you going to waste because of the resistance of the wire? And you're actually just heating up the wire instead of delivering the energy to the load where you want it to be. So here's the resistance per length from the table. 14 gauge wire, 2.5 ohms per 1,000 feet. We have 100 feet of wire, so it's only 50 feet away, but we have two lengths of 50 feet. So that current has to travel 100 feet, and all 100 feet will be heating up. Okay, the resistance then is a quarter ohm. That doesn't seem that bad. You have a quarter ohm resistance. That should be just fine, right? But when you have a current of 22 amps, the power loss to the wire is actually 127 watts. That's huge. And the power from the panel, if it's 400 watts, you're actually losing 32% of your power to the wire. That's a lot, right? Big percentage of your power is not going to the load where you want it to be. So let's suppose you browse around some more online and you find this $140 wire, which is 10 gauge, right? It's almost twice the price. And here's the resistance per length of that 10 gauge wire. Right? And so you still have 100 feet, and the resistance then of that wire is 0.1 ohms. Well, that's less. That's good, right? Instead of a quarter ohm, you're a tenth of an ohm. But you still have that same current, 22 amps. So the power loss to the wire is 50.3 watts. That's still a lot of power, right? You're losing a lot of power to metal, which is supposed to be a perfect conductor in our circuits class. It's not. So this is something to consider, but it's less power loss. So we have 400 watts from the panel. That means only 13% of that power is lost to the wire. Okay. So the whole point of this exercise, the slide I'm showing up, is that wire resistance matters at this higher current and longer distances. So if you have some project where you have a power supply that needs to be far away from its load, and you need a certain voltage at that other end where the load is, you have to consider the voltage drop. And if it's a portable or battery powered or solar powered application, power lost to heat in the wire is a consideration. But so great, let's use the largest possible wire we can. Well, there's disadvantages to that because that wire is more expensive, right? So you think about it, what would your decision be? Would you go cheaper on the wire and give away 32%? Well, that means you paid for 32% too many solar panels, right? So you actually paid, part of your solar array is just going to heat up the wire, and you bought it to heat up the wire. Or do you go with a more expensive wire and have a better power efficiency? So there's no right answer here. It's just going to make that decision as an engineer. Your decision might be different if this is a 4 kilowatt system, right? If you had 40 panels instead of 4 panels, right? That's a lot of power loss. Panels are expensive, you know. So again, I'm just showing you some inputs to a trade you might make. And also, cost isn't only a factor. Weight and temperature are factors. If you have uh, a higher temperature, like I don't know, it's in the desert versus up farther north, you might have higher resistivity at peak sun times, which is when you want the solar panels to be operating. And weight is consideration. So if this were an aircraft application and you care about delivering power from an alternator to a battery to the rest of the avionics or other power systems, um, then you would care. Um, so weight, and you don't want an airplane to get heavier because then you're reducing your payload to your airplane. So you gotta figure out what all the trades are. It's not just cost and power loss, it's also weight, temperature, and other things. So why does the resistance of a wire change with temperature? Yeah, so um, basically the resistivity goes up, and without going into the physics too much of that, you get higher electron motion when the wire gets hot, and the resistivity uh, goes up, and that's going to be result in a higher resistance for the overall wire. Okay. So, okay, great. So you have that, and then you want to, what's an alternative, right? So let's figure out an alternative to this because you're still losing a whole lot of power in the wire. So what else can we do here? We have the same 4 solar panels. You have the same load, the same charge controller, the same length of wire. Um, and each panel is still 100 watts at 18 volts. But instead of connecting these panels in parallel, let's connect these panels in series. Okay, so let's do this, right? Let's connect all these in series. And so this is like connecting sources, voltage sources in series. So you run the KVL equation around this and you get 72 volts between these two wires. So it's no longer 18, you have 72 volts at that connection to the end of the wire. So now you have 400 watts still. There's still 400 watt solar panels, but you're operating at 72 volts. So your current is not 20 amps or 22 amps. It's down to 5.5 amps. Okay. So will this destroy the controller? No, because this particular controller handles 100 volts. So you'll see controllers that handle around 100 volts. Some are a lot lower, but many solar charge controllers will handle that. Okay, so let's go grab the same wire and see what happens here. You have same resistance per length, the same length. Here's the resistance, same resistance. The current now is not 22 amps, it's 5 amps. So the power loss to the wire is now 7.9 watts, and that's only 2% power loss. Okay, so here for 10 gauge wire, here's the resistance per length, 10 gauge wire, same length. Here's the resistance. The current again is 5.5 amps. Okay. And the power loss to the wire there is 3.1 watts, which is only 1%. So just by changing the configuration of those solar panels from parallel to series, dropped the power loss to the wire by a huge amount, right? Our power efficiency got a lot better. And now the difference between 14 gauge and 10 gauge wire is only 1%, right? 2%, 1%, it's 1% difference. So maybe it's not worth the more expensive wire, right? So in the other case, it might have been worth the more expensive wire, the heavier wire. So the um, higher voltage that you use for power transmission is generally more efficient because you have lower current needed. So that's why you see these high voltage power lines up really high off the ground, and they're, 700 kilovolts as various voltages. But um, that lets you deliver the same amount of power at a lower current because you're using higher voltage. That's the whole premise here, right? So why don't you just use high voltage everywhere? Just let's keep going up in voltage. Well, it becomes very dangerous to people. So that's why we only have we use 120 volts RMS in our house because it can kill you, but it's not going to kill you instantly like a 1,000 volts would or higher. Okay, and but the system components need to be rated for the higher voltage, and safety is a factor. If you the safe range is considered around 50 volts. If you're below 50 volts, like 12 volts, you won't generally be feel a shock. If you go above 50 volts, then that can get dangerous if you touch the terminals. Okay, so this is an example. It's really to show trades that we can reduce costs significantly. We can reduce um, power loss significantly. We can reduce weight if this were wiring in an airplane uh, significantly just by considering how we configure the components of the system. Okay, here in this case for higher voltage. If you had more solar panels, oh, let's put them all in series. The problem is once you exceed 100 volts, you would destroy the solar charge controller. So you could do this. You can do a combination of series and parallel, right? You could do an array of 4 and then multiple arrays of 4. So they're all 72 volts and then connect them together. And there are different considerations when you have solar panels in parallel. If they fail open, then you lose, let's say one panel fails, you lose 25% of your power availability, um, but the system keeps operating. Here, if you lose one of these panels and they gets hit by hailstones and one of them fails as an open circuit, your whole system is down. So this is more power efficient, but can be more vulnerable. Okay, so lots of trades to consider here. All right. So that was all about Ohm's law. That was the review of Ohm's law. And I wanted to show some practical applications where something as simple as Ohm's law shows up with some pretty significant consequences. So let's go to a review of reactive components. We're going to talk about capacitors and inductors. So you probably recall that if you have a couple conducting plates separated by a dielectric or an insulator, dielectric is an insulator, um, you have a capacitor. Here's the schematic symbol for a capacitor. Here's the voltage and the current for that capacitor. Right? And in the time domain, the relationship between voltage and current is I is equal to C dV dt. Right? So capacitance in farads times the derivative, the time derivative of voltage is the current. Okay, so current is 0 when V is DC. You take the derivative of a constant, a DC value, and you get 0 current. And current only flows when V of t is time varying. Okay, so current doesn't actually flow through the capacitor. From the outside world, it looks like that. It looks like current's going back and forth through the capacitor. But really what's happening is the capacitor's charging and discharging. So charge is flowing into the capacitor from one terminal. It charges, and then if you have an AC current, it's alternately charging and discharging that capacitor. So it looks like current's going through it, but it's really just a charge and discharge state. Using phasors and impedance, if you have phasor voltage and phasor current, then we define not that component not with capacitance, but with an impedance, Z sub C. And so the impedance of that capacitor is minus J times 1 over omega C. C is the capacitance. Omega is the angular frequency of a sinusoid. Usually we're working with sinusoids here. And V equals IZ, right? Looks like Ohm's law. And then the impedance of a capacitor falls with increasing frequency. So we're going to talk about that. Capacitors can be used to filter out noise from power supplies or sensor voltages. And we do that because of this characteristic that the impedance falls with increasing frequency of a capacitor. Okay, so here's some example capacitors. These are ceramic capacitors. You have probably something that looks like this in your kit, maybe something that looks like that. They come in surface mount packages and these leaded packages, through-hole packages. They're small size, they're low cost, and they're usually small capacitance values. Okay. If you need larger capacitance values, you go to electrolytic capacitors. So here's, you have capacitors in your kit, you will, that look like this. These capacitors are polarized, and usually they have higher capacitance values, but they have a large tolerance and drift of capacitance. If you know, for example, you might have a 100 microfarad capacitor, and it might have a 10 or 20% tolerance. And oftentimes when you use these capacitors, you don't care so much about the exact value. You just care about its order of magnitude so that you can get maybe an impedance low enough to work in a filter. Notice in lab, when you're working with this capacitor, that these are polarized. You'll see usually a minus sign next to one of the leads. Sometimes I've seen a plus sign next to one of the leads, but pay attention to the polarity, because if you put these in with the wrong polarity, after a while, you can degrade the capacitor. It'll stop working. And in lab, pay attention to when you're building up your motor driver circuit. You'll get to that. Pay attention to that polarity of the capacitor and the noted polarity on the schematic and the circuit board. Mica capacitors. So mica capacitors are generally high voltage capacitors. And we'll use these sometimes for radio frequency circuits. And they're typically smaller capacitance values. And they can be tighter tolerance. And then these are variable capacitors. You can see these interleaved fins, and you turn this knob, and that adjusts the amount that those fins overlap. And so if they're completely overlapped, you get a high capacitance. If they're completely not overlapped, that's a low capacitance. So you can build a variable capacitor. And that's a big capacitor, or maybe a high voltage tuning circuit. Here's a miniature adjustable variable capacitor working on the same principle in a different package, and a lot smaller, meant for a circuit board. Okay. So when you need to tune a circuit, you would use those types of capacitors. But when selecting a capacitor, here's what you need to consider. You can't just go say, I need a 10 microfarad capacitor, and just grab any capacitor. Typically, you have to consider not only size, will it fit, but consider the capacitance value, of course, and its tolerance. Do you really care if it drifts by 10 or 20%? Note its polarization, if it's electrolytic, and also notice its maximum voltage rating. You can get, for example, the capacitor that's in your kit in an electrolytic package like this, and I think it's 100 microfarads. You can find those in 6.7 volts or different voltage values. I think you have a 50-volt capacitor, but if you put a 6-volt capacitor in a 12-volt circuit, eventually you're going to have problems. So you got to pay attention to more than just the capacitance value of a capacitor. Okay. All right, so here's a common application for a capacitor. Filtering either for a power voltage or a signal voltage, like from a sensor. And also, blocking a DC voltage is also common. So let's suppose you have a source, DC source. Here's the Thevenin equivalent, we'll talk about that, of a DC source. And then you have a DC load. And you put a wire between. These could be test leads or jumper wires or circuit board traces, the copper traces on a circuit board. Could be a breadboard connection. Could be wires across some kind of vehicle. And that wire, as we talked about, is not resistance free. It has some resistance and it also has some inductance. And what you've created there is basically an antenna. You've created a way for electromagnetic fields to cause a voltage on that wire, right? We call that noise, external noise. Okay, so you get this noise voltage across that wire. And noise on power supply voltages at loads, like let's suppose this load is a signal amplifier. You have a sensor that needs an amplifier, times 10 amplifier. Maybe it's an op amp. And if you remember if you took my class and you built the op amp circuits, you put decoupling capacitors at the VEE and VCC nodes on your board, on your breadboard. But if you have a noisy DC voltage, that can cause noisy signals out of, let's say, an amplifier. You could have noisy sensor signals, noisy audio, etc. Noise on digital lines, like if you have some digital chip and you don't have a clean power supply signal, that can cause errors in the values of the digital signal. So this is an analog and a digital problem. And what we do is we use capacitors, and when we use them in this way, we'll call them decoupling capacitors. It decouples the noise from the circuit. So we use these decoupling capacitors to reduce noise from the external environment. And it does that by providing a low impedance path to ground. So this plot here shows the magnitude of the impedance, right, of a capacitor, and here's the frequency in hertz. So if you have 100 microfarad capacitor at, let's see, 10 hertz, you have just over 100 ohms impedance magnitude. At, let's see, that was at 10 hertz. At 100 hertz, you have just over 10 ohms. At 1,000 hertz, you have just over, that's not, yeah, 1 ohm. Trying to read this plot here. Okay, so you can see the magnitude of the impedance falling, the magnitude of the reactance falling as frequency increases. And so what you're going to use that, you're going to take that property, that characteristic, and essentially you're creating this low impedance path to ground. It's like you're shorting from this node above the load down to ground, and that low impedance path causes the noise voltage to be a lot lower across this DC load. So when you hear decoupling capacitors and you see that in lab, that's what this is. Capacitors can also supply energy during transient loading events. So, you have a motor that you're turning on and off, or a transmitter you're turning on and off, and that's what this DC load might be. Well, because of this resistance right here and this inductance, if you get a rapid change in the load, like something turns on the right here, then you're going to get a voltage drop across the resistance and the inductance as the current's trying to change. And so what can happen is if you have this capacitance close enough to the DC load, that capacitor's charged energy can supply the load with energy, with power, while that transient event is occurring. So this will reduce the fluctuation of voltage at the DC load if you have a capacitor at that load. So reducing noise and supplying energy during transient loading events. And capacitors are also often used to pass AC signals. and block DC signals. So if you have to couple an audio signal into an amplifier and you want to isolate DC on either side of the capacitor, you can do that. You just have to pick a big enough, large enough capacitor so that its impedance is low enough compared to what you need. Okay. And so it's good practice to use one or more decoupling capacitors near the power pins of ICs. So that's what we did in the circuits lab if you took my circuits class. We put capacitors right next to the op amp on its power pins. And you'll see this commonly on circuit boards and in other circuits. You'll see capacitors where they appear they don't really do anything because they're sitting there on a DC line, and capacitors should be open for DC. The fact is there's more than DC on that wire. There's AC being conducted in from external sources or received from external electromagnetic sources. Okay. So in practice, let's take a look at some decoupling capacitors. Here is a schematic of your lab project that you will start this Friday. Right? It's a microcontroller board, a bunch of sensors, a couple sensors, DC to DC converter, battery, motor. And so what you'll see are all these capacitors, and they don't look like they're doing anything. They're on either DC nodes, lines, or they're connected to slowly varying, like temperature. It's a slowly varying line. So you see these capacitors here. The intent with all those capacitors is to reduce noise. And so you have this motor here. Motors are noisy devices, especially brushed motors. Brushed motors, if you remember from Intro to Circuits, they have a commutator and a piece of metal, a brush that rubs against it, and the current starting and stopping. That's usually emitting some kind of some kind of EM field causing noise throughout the rest of your circuit. And also the start and the stop of the current and the sparking going on inside that motor causes conducted noise too into power supplies and nearby circuits. So these capacitors reduce that noise. So you could try to take them all out of your project and it might work. Sometimes it might not. Trust me on that because I designed this. I put it together and sometimes things weren't working. You measure the voltages with an oscilloscope and you see, oh, there's an AC voltage coupled into this line and the IR sensor doesn't like that, or the microcontroller is triggering on a signal I didn't expect to be there. Okay. And you'll see so this is your project on the left. This is an Arduino Uno schematic on the right. And so you can see the microcontroller and some supporting integrated circuits here. And I've circled many, maybe all of the decoupling capacitors, right? Here's one on the upper left between the 5-volt power supply and ground. You have a 0.1 microfarad, 100 nanofarad capacitor. 0.1 microfarads is very common for relatively low speed devices like this microcontroller, like your project. It does a good job at filtering out. It's the right impedance for the frequencies that you would expect showing up on these DC lines or slowly varying sensor voltages. So you can see them all here. Here's a 3.3 volt decoupling capacitor. Here's another one. Right next to that chip, you have another decoupling capacitor. Here's another one right next to that chip. And usually, physically, you put those very close to the chip you're trying to protect. Here's what is that? That's an analog reference for an analog to digital converter. It also has a decoupling capacitor right there. So they become important. Okay. So the main purpose, the takeaway here of these capacitors is to remove unwanted AC noise from the DC voltages. You want DC or slowly varying AC, very slowly varying voltages. And these capacitors do that, and they supply energy during transient loading events. All right. Okay, so here's an example. Just want to finish this off with something practical here. If I have a sensor with a 10 kilo ohm output impedance, and I have a data logger with a 10K ohm input impedance, right? And I just connect them together. And I did this, I actually did this on a bench. I had a 10K output impedance on a voltage and a analog to digital converter with a 10K input impedance. And so this is the oscilloscope trace with no capacitor. Okay, so you can see, let's see, what's the timing here? 500 microseconds per division, 500 millivolts per division. And we have a 3-volt DC voltage, except look at all that noise on there. And that noise is about 77 millivolts RMS. I've got a measurement somewhere on here. Okay, but what happens if we add a capacitor, just a 0.1 microfarad capacitor close to that data logger? This happens, you get this. So same circuit, just add that capacitor. You still have a 3-volt DC voltage, but you have much smaller RMS noise, so 6 millivolts. Okay, so that's huge. That's a big difference. So adding just that 1.1 microfarad capacitor reduced the noise voltage by 92%, reduced the noise power by 99%. And, do you need it? Do you know? If you have a device that is intended to have DC, then having more than a few millivolts of noise can be bad, especially on circuit boards. All right. So that's an example. There's that kind of a, capacitor review. We talked theory in the circuits class. Here are some less theoretical, more practical applications of capacitors that show up everywhere. All right. So let's review inductors. Inductors, you have a coil of wire. The coil of wire creates a magnetic field. If you try to change the current through that coil of wire, you get a time-varying magnetic field because of the time-varying current. A time-varying magnetic field through a coil of wire induces a voltage. Okay, that's Faraday's law. So here's the schematic symbol with voltage and current in the time domain shown. Here's the relationship between voltage and current. So, right, if you try to change the current, if you try to change that current, that derivative is going to be non-zero, so you're going to induce a voltage. And L is inductance, which is calculated from or determined by the size of the coil, the number of turns, the material that's used as a core, spacing of the turns for a given inductor. Okay, so the voltage is 0 when I of t is DC, right? Because if I have a DC current, then the derivative is 0, so I get no voltage. And the voltage is non-zero only when I of t is varying. Okay. And in using phasor notation, here's voltage, current, and impedance of that inductor, where impedance is J omega L. And then V equals IZ. Looks like Ohm's law, but with complex numbers. And you can see that the impedance of an inductor increases with increasing frequency. So you can actually use inductors to block AC at higher frequencies because the impedance goes up. Okay, so some examples here. Here are some cylindrical or solenoid inductors. Here's an air core inductor. Here's an probably a ferrite core inductor there. Just a coil of wire. They're small and they're low cost. Here's a toroid. If you need high inductance, then you might use a toroid, and they could be tiny, fractions of an inch up to inches in diameter. And that contains the magnetic field and makes the the inductance higher for a given number of turns. There's surface mount inductors, coil of wire around what's called a bobbin here. Here's some enclosed, encapsulated inductors. Okay, and they're meant to mount on printed circuit boards. Here's some axial through-hole inductors. They look like this. You can read that color code, figure out their values. And they mount on through-hole PCBs. And just like capacitors, when you select an inductor, you've got to select not only the inductance value, but also the tolerance, the frequency, and the loss characteristics of that inductor. And also from a mechanical perspective, size and weight, you're probably not going to take a big toroidal inductor on a big toroid core and fit it into a cell phone, right? So if you're designing electronics that have to fit into a small package, then you've got to consider when you see an inductance of maybe millihenries, some big inductance, then and how much power does it have to handle? You might have to look at alternatives because of mechanical constraints. So, all right, so I've gone a minute over on time here. And so let's end class right now. And in closing, please see Canvas for upcoming assignments. You have lab homework 1 due, and then lab 1 will be held this week. So I will see you in lab on Friday. Also see the ITLL workshops. If there's anything that we talked about, like soldering or microcontrollers that we talked about are topics of this class and you want a refresher, be sure to sign up for one of those workshops as maybe a refresher or an introduction. What else? Let's see. And just expect to come into lab this Friday, form your lab group, and we'll get started there. So I will start office hours right after class. So if you'd like to chat, just stick around. If not, I'll see you next time. Have a great night.